Okay, continuing right where we left off before. I was finding this value for delta here, so this is all correct. I was finding this value here. I forgot to multiply this or divide this by 2 because we have 2 EI here. So this is actually going to be equal to 32 EI. Okay, and finally, this is 0 times this triangle, so I don't need to include the last arm. So the deflection at this point, due to this load, is going to be equal to delta P1 of 1 plus delta P2 of 2 minus delta P3, P1 of 2, P1 of 3, plus delta P1 4. This is every term that I've found so far. This one, this one, this one, and this one. And what I should get when I'm done with all that is that delta C is equal to 31 PL cubed on 128 EI. Okay, this is just due to this system. I need to do the same thing with the P2, P3, and R systems. But the P2 system is very easy. The P3 system, I don't have to do this subtraction, this funny subtraction stuff. So you shouldn't have too much trouble with doing the P2 and P3 systems. Your R system is identical to your Q system, except everything, you're going to multiply everything by R. So you already have this system, and R times Q should be fairly straightforward. So at the very end, you're going to end up with, and I should say that delta C, this is delta C, C due to P1. Sorry, this is delta P1 at C. Deflection at C due to P1. At the very end, I should end up with 4 values. So I should end up with delta P1 plus delta P2 plus delta P3 plus delta R equals 0. And I'm going to solve this. I can get R equals something. Now, I was doing this a couple different times, and every time I do this, I end up getting a different result for some reason. And I was checking this on the computer, and every time I do it on the computer, I seem to get a slightly different result. When I did the computer analysis the first time and I sent out the solutions, I had forgotten to increase the horizontal stiffness to 2 EI as opposed to just leaving it at EI. So that changed my results slightly, but my results still do not match the solution that I'm getting from the computer. That said, if you do this the way I did, I ended up getting that R was equal to 31 on 56p. From here, and that is equal to 31 divided by 56. That is equal to 0.5536p. Which I think is close to what I gave out online, but your mileage may vary. What's important here is that you at least figure out how to use virtual work to get the reactions. Once you have the reactions, even if there are slight mistakes in your reactions, your reaction should be somewhere between 0.5 and 0.6p. This is assuming that you remove the reaction at dx. Dx should be somewhere between 0.5 and 0.6. All right, as always, let us know if you have any questions. I think that is, this is probably the most complicated problem you'll see. I don't think you'll see something like this on the exam. So if you're getting something that's about this, let's say you get 0.52 or 0.54 or maybe even 0.58 or something, I would just use the value that you have and keep working from there. Because if you're getting a value that's about that range, you're obviously doing the right procedure. And if you're doing the right procedure, then I don't think you gain that much by going back and trying to figure out where exactly you messed up. And my solution for this ends up coming out to like 4 pages or so. I don't think it's worthwhile to go through and check every single one of these because there's more the trade-off for this. How should I say this? There's like diminishing returns on this problem, where you get most of the benefit from this problem from the first few passes through. So if you get somewhere between 0.5 and 0.6, just use that value. Don't worry about fixing up the details too much. You must still make a serious attempt though on this problem if you want to get credit for this problem. You can't just copy the solution that I posted online. Make a serious attempt to get the reactions, and then we'll give you as much credit as we think is warranted. All right, let us know if you have any questions.